Okay, so let's unpack this. For years, we've sort of treated these complex AI models like high-performance black boxes.
Right. They give us these incredibly accurate predictions, which is great.
Yeah, in finance and engineering and, crucially, in these really high stakes fields like healthcare. But they can't tell us how they got to that answer.
Exactly. And if a system is, diagnosing a patient or deciding who gets a loan, that black box suddenly becomes a huge liability if you can't open it up.
That's the core tension, isn't it?
It is. So our mission in this deep dive is to synthesize the concepts you need to know, the definitions, the absolute need for this transparency, and then the mechanics behind the tools professionals are using right now.
We've got sources that give you a direct route into understanding how the leaders in this field are building AI that's transparent, not just, accurate.
And we're going to tear open the two big ones, Lime and SH.
This is about giving you that shortcut to understanding how people verify trustworthiness in systems that could be making life-altering decisions about you. So let's start not with a definition, but with the necessity. Why now? Explainability isn't just some academic thing. It's essential for actually using these things in the real world.
It really is.
Yeah.
And our sources point to four main pillars for why this is just non-negotiable anymore.
Okay.
The first two are all about acceptance and fairness. You simply can't deploy a complex model unless the people using it, doctors, bankers, regulators, have trust in its reasoning.
If you can't trust the mechanism, you can't trust the output. Makes sense.
And right alongside that is the critical need to detect hidden bias. Models learn from historical data, right?
Right, and history's full of biases.
Exactly. So if that data has systemic biases, the model will learn and probably even amplify them. Explainability gives us the tools to see that happening before it causes real harm.
So that's the user and societal side, but there are also huge needs for the developers and, I guess, the legal teams, too.
Oh, absolutely. If a model starts acting weird in production, the ability to trace its logic is a vital debugging tool for the engineers. You can see which feature went rogue.
And that leads to the fourth pillar, which I imagine is becoming the biggest driver, regulation.
It is. Regulatory bodies, like the FDA for medical devices, they are now demanding these verifiable explanations before they'll approve an AI system.
So if you can't explain it, you can't ship it.
Pretty much. It's now a requirement for compliance.
Okay, before we move on, there's a quick distinction that I think trips a lot of people up. Interpretability versus explainability. People seem to use them interchangeably.
They do, all the time. But the sources make a really helpful distinction. Think of interpretability as the raw mechanism. It's designing the model to be transparent from the start, turning that black box into a glass box.
Okay, so interpretability is like being able to see all the gears and levers inside a complex engine. You can literally see the process.
Precisely. Explainability, on the other hand, is the human understandable outcome of that. It's taking that raw transparency and turning it into a clear story.
A narrative.
Yeah, a narrative reason that a doctor or a CEO can actually understand. It's saying the engine light came on because the third gear shifted late, which caused the pressure to drop.
Got it. One is the raw visibility, the other is the distilled reason, which brings us to this core dilemma, the unavoidable trade-off.
Right. As models get more and more complex, think massive neural networks, their performance usually gets better. But that complexity has a cost.
The trade-off is clear. Better performance usually means worse interpretability.
It does. When you have billions of parameters, you might get incredible accuracy, but figuring out why any single one of them shifted the final answer becomes, well, almost impossible.
Okay, so to navigate that trade-off, we first need to understand the scale we're working at. Our sources talk about global versus local interpretation.
Right. Global interpretation is when you want to understand the forest, not just a single tree. It's about the complete overall behavior of the model across the whole data set.
So in that credit risk model example, global interpretation would tell us that generally things like income and credit history are the most important factors for the entire customer base.
Exactly. It tells you the model's general strategy. Now, local interpretation is the opposite. It couldn't care less about the whole population. It aims to understand how the model made a decision for one single specific instance.
And that's the key. That's what makes tools like Lime and SHAP so critical. It moves from what does the model usually do to explain precisely why my loan application was rejected.
Yes, That local focus is what lets us audit for individual fairness.
Okay, here's where it gets really interesting, because getting that local explanation from a black box is hard. You need some clever tricks, and the first big one we'll unpack is Lyme.
Local interpretable model agnostic explanations. And that model agnostic part is key.
What does that mean exactly?
It means Lyme is like a universal translator. You can apply it to any machine learning model, whether it's brand new or decades old. Doesn't care.
The genius of it, then, isn't trying to understand the whole black box, but making a little local approximation of it. The whole surrogate model idea.
That's it. Imagine the complex model is a massive, opaque mountain range. You just want to understand the slope at one single point.
Okay.
Lyme says, I'm not going to map the whole range. Too hard. Instead, right around your point, I'm going to build a tiny, simple, flat shed, a local surrogate model that just approximates the terrain in that immediate neighborhood.
And because that shed is a simple model, like linear regression, we can just read its coefficients and see what was most important for that one prediction.
It's an honest, local approximation of a global complexity. And to get the data to build that shed, Lyme uses something called the perturbation technique.
Perturbation. So it's basically just testing the boundaries, right?
Right.
It takes the original data point and then just makes a bunch of slightly modified versions of it.
Yep. It just nudges the data a little, changes one feature slightly to see how sensitive the big model's outcome is to that tiny change.
So let's walk through it. Step 1, you pick the data point you want to explain.
Then Lyme generates all those slightly altered versions, the perturbations. And it feeds all of them into the original black box model to get predictions for each one.
So now it has a bunch of slightly different inputs and their corresponding outputs from the complex model.
Correct. Now it uses that data to build the simple translator. It gives more weight to the perturbed points that are closest to the original one.
Because they're the most relevant to that local area.
Exactly. Then it just fits a simple, interpretable model to that weighted data.
And the coefficients of that simple model are the explanation. They tell you what the big, scary model was paying attention to in that one specific spot.
It's a 6-step dance that gives you a human-readable reason from an impenetrable model.
That's a fantastic mechanism. So now let's shift gears a bit to S-shape Shapley additive explanations. Lyme is functionally clever, but SHAPP comes with a different kind of rigor. It's built on a really strong mathematical foundation.
It is. SHAP's foundation is cooperative game theory.
Okay.
The analogy is really useful. Imagine your model's features, glucose, BMI, age, are all players on a team working together to produce the final prediction.
And SHAP's goal is to figure out how much credit each player deserves for the final score.
Precisely. It calculates the Shapley value, which is a method from Nobel-winning mathematics for fairly distributing the payout among the players.
But wait, if a model has thousands of features, how is that practical? Does SHAP really have to check every single combination of features to figure that out?
And you've just hit on its main drawback.
It sounds incredibly slow.
It is. It's often much, much slower than Lyme. That's the trade-off. To guarantee that fairness and consistency, the Shapley value calculation really does involve considering all possible feature permutations.
So for any given feature, SHAP calculates the prediction with it and without it across every other possible combination of features.
That's the core idea. The Shapley value is the average difference in the prediction caused by adding that feature across all those different combinations.
So by averaging it out, it gets a really robust measure of importance.
Exactly. It ensures the importance is consistent, which is why SHAP has become the gold standard for high-stakes audits. And, like Lyme, it's model agnostic and gives you those crucial local explanations.
That framework is clear, but let's anchor this in something concrete. We need to look at the practical findings from that Pima Indians diabetes database case study the sources used. This is where theory hits reality.
Right, and the SHAP summary chart is probably the most powerful way to see a model's behavior. It takes all those local explanations and combines them into one global view.
Okay, let's break down this visualization because there's a lot going on. On the y-axis, you've got the features sorted by importance with the most important ones at the top.
Right, and then the x-axis, that's the SHAP value itself. This is all about impact. A positive value, on the right, means that feature pushed the prediction higher, so increase the diabetes risk.
And a negative value on the left pushed the prediction lower.
Correct, and then you have the color. Each dot is a single patient, a single prediction. Red dots mean a high value for that feature, blue dots mean a low value.
And this is where the aha moment happens, right?
This is it. You look at a feature like glucose, and you see this mass of red dots, high glucose levels, clustered way over on the right side. with high positive SHAP values.
It's immediately obvious. High glucose systematically increases the model's prediction of diabetes.
You see the model's logic right there. And the case study's findings were crystal clear from this chart. Glucose is, by far, the most important feature. BMI is a close second.
But it's not just that BMI is important, it's that high BMI is what pushes the risk score up. That specificity is what makes it actionable.
And, just as important, it helps you see the noise. Things like skin thickness and insulin were at the bottom, with SHA values all clustered around 0.
Meaning the model was basically ignoring them.
Right. It gives a doctor the confidence to focus on what really matters, glucose and BMI.
So we've essentially taken a black box model and used SHA to create a complete visual audit of its logic. We know what matters, how much it matters, and which way it pushes the prediction. That's powerful.
To tie it all together, explainability, using tools like Lime and S-Shape, is really the next necessary step for AI.
Yeah.
It moves the whole conversation beyond just, performance metrics, beyond 99% accuracy.
It provides that assurance of fairness and logic that you absolutely need before you can trust these systems with important decisions.
Exactly.
So you now have the conceptual framework to audit the logic of almost any model you encounter. We've defined the difference between global and local, understood Lime's clever surrogate model approach, and grasped the mathematical rigor of SHAP's game theory.
It's a complete toolkit for opening the black box.
So what does this all mean for the future? We've seen the trade-off is real, performance versus interpretability, but in these critical high-stakes situations like that diabetes predictor, at what point does absolute verifiable explainability become more valuable than a tiny fractional improvement in performance?
That's the central question.
Where do you draw that line? That decision is at the heart of every AI deployment strategy now, and that's the question we'll leave you with today.